Okay, so this is for a real analysis question, part of the harder 3-unit section in the Extension 2 course. So part A says, prove that a squared plus b squared is greater than 2ab. So how are we going to go about this? We'll take a look firstly at what we know about this problem. So RTP is cool. So we're trying to get to this. How are we going to get to this? So the one way we can do this is work backwards, essentially, and show our working as a way of proving this, and just work backwards from our work. What I mean by that is a squared plus b squared minus 2ab is greater than or equal to 0. Then we have a minus b all squared is greater than or equal to 0. And then this is essentially a given fact because any number you square is always going to be positive. Okay, so in terms of this, what we have to do is just rewrite this backwards, essentially, and we say that this is proven, I guess, which is kind of, makes sense. Cool. And a squared minus 2ab plus b squared is greater than or equal to 0. And then we have a squared plus b squared is greater than or equal to 2ab, which is what we needed to prove. So we're going to say QED. Cool. Part 2 asks us to prove that a squared plus b squared plus c squared is now greater than or equal to ab plus bc plus ca. So how are we going to do this part? This one's a little more trickier to see. We have to essentially use, usually these type of questions, we are meant to essentially use each previous part for the next part. As you'll see in this question, it's a pretty usual trend with these type of questions. So how are we going to go about this? Proving that a squared plus b squared plus c squared is greater than or equal to this. So there's two ways you can go about this. You could try to get an idea. So we do notice that a squared plus b squared plus c squared we can get that by, I guess, expanding this, because we do know this is greater than 0. This is a given fact, and we can move from here to essentially get somehow and manipulate that and get to this expression here. But that would be a little bit tedious. Another way we could go about it is using part I. So in part I, we proved that a squared plus b squared is greater than 2ab. Using that same logic, we can use that to prove this. So a squared plus b squared is greater than 2ab. Cool. So a and b don't have to, they don't mean anything. They just stand for numbers, right? So technically I can interchange them as I like. So a squared plus c squared is greater than 2ac. A squared plus b squared is greater than 2ab. And then c squared plus b squared is greater than 2bc. Cool. So now I have these three kind of versions of what I needed to prove. And what I'm going to do is add all of them. So this will be 2a squared plus 2b squared plus 2c squared is greater than or equal to 2ab plus bc plus ac. Cool. Then we'll divide by 2, and then we have that expression that we needed to prove. Cool. I guess that's also QED. Okay, so that was not too bad. Let's look at part 3. Part 3 says that we're given this expansion of a cubed plus b cubed plus c cubed, and we're essentially required to prove this. So if you notice that this part is exactly this part, just with a greater than or equal to sign. So what I'm thinking usually here is that we use the given component and use the previous parts, what we required to prove, and do some manipulation to essentially get to this stage. Cool. So what we're going to do, if you notice as well, you see that this here is the same as this, just obviously on the other side, like we moved this part to the other side. And we just added an a plus b plus c term just to it. Cool? So what we're going to do for part 3, we're going to write out what we got in part 2, which was that a squared plus b squared plus c squared minus ab minus bc minus ac is greater than or equal to 0, which is a given fact since it's from part 2, and that what they gave us, which was the result that a plus b plus c times this whole thing, a squared plus b squared plus c squared minus ab minus bc minus ac, this whole thing is equal to a cubed plus b cubed plus c cubed minus 3 times a, b, and c. Cool. So this expression, which is essentially what we're trying to prove, but with a obviously a greater to equal to sign there. Cool. So how we're going to go about that is we are probably going to now sub in. Well, we're going to start off with, I guess, part 2, what we had in part 2. So let's just say part 2, this is what they gave us, a squared plus b squared plus c squared minus 2, not 2ab, minus ab minus bc minus ac is greater than or equal to 0. And what we're going to do is multiply both sides by this term, this a plus b plus c term. So a plus b plus c, a squared plus b squared plus c squared minus ab minus bc minus ac is greater than or equal to 0 still, because we can do this essentially because a plus b plus c is all positive, and multiplying by 2 positive numbers is not an issue, and anything multiplied by 0 is still 0. Cool. So now we can essentially sub in this part, because obviously that's what we have now. And subbing in that, we get that a cubed plus b cubed plus c cubed minus 3abc is greater than or equal to 0. And then pretty easily we get our expression that we were required to prove. Cool. So that's part 3 now done. Okay. So I think that was for the easier parts of this question. Now if we look into it, we can look into parts 4 and 5, and we're required to prove something a little bit more trickier here. So if we look closely at this, it says by making a suitable substitution into what we got in part 3, so as you can see it's still the same trend of what we got in the previous question we have to use in this question, we're required to show that this expression holds. So essentially, it may not be obvious at first, but if we look carefully, we can essentially make a substitution such that this equality can kind of be satisfied. So what I'm going to do is, again, write out what we got in part 3, which was that a cubed plus b cubed plus c cubed is greater than or equal to 3abc. It's a pretty nice expression. And essentially I'm going to do some manipulating, or I guess substituting, because it's asking for a substitution, and kind of show this. So we do notice it's very similar to what we have and what we need to prove, because it's just this, I guess. Just go again, x, y, z. Okay, so we see that it's very similar in the likes of, it's just these terms, but obviously they don't have cubes around them, and it's the same last part, but obviously no cube root in what we need to prove. Cool. So what I'm thinking is that in this question, we obviously have a cubed. We need to let a cubed equal something, and same with b and c, to get this. So what we need to let is obviously let a cubed equal x, right? And this means that obviously a equals x to the power of a third. And similarly with b cubed equals y, which will equal y to the third, and c cubed, which equals z, and c will equal z to the third. Okay, so now writing out the same expression, we get x to the third to the power of 3 plus y to the third to the power of 3 plus z to the third to the power of 3 is greater than or equal to 3 times x to the third times y to the third times z to the third. Cool. So now we can see how this essentially lines up with what we needed. So it's a very nice equation there. And that's essentially it. That's what we needed to prove. Now we can move on to part 5, which says, suppose this equality holds. So they've given us this is the given term. We need to prove that this now holds. Okay, so looking into this, there may be quite a few ways to go about this, right? But obviously we want to make use of this last part and this inequality, that they've given us to essentially deduce this. Okay, so it may not be obvious, again, what we need to do, but let's just write everything out that we know. So we have x plus y plus z. Sorry, let me change this to a white. Greater than or equal to 3 cube root of x, y, z. And they've given us that obviously x plus 1 is y plus 1 and z plus 1 is equal to 8. Cool. So again, you will notice that there is some similarities, some differences between what we need to get. So we need to prove eventually x, y, z is less than or equal to 1, I think. Yes. Right. So again, you can notice that there's x, y, z here and x, y, z there. But obviously this is in a different manner, because it's talking about these additions somehow relates to a multiplication with 3 and cube roots. So how are we going to get rid of all this and obviously make it something nice and easy like that? We have to make some more substitutions and adjust these terms to essentially get to what we need. Cool. So what I'm thinking, we could go about this many ways. Okay. So what I'm going to do, I'm going to let x equal x plus 1, and obviously y equal y plus 1, and z equals z plus 1. I can do this because 1 is obviously positive, and it's still holding true with the statements that they've given us, that we have to have x greater than 0, y greater than 0, and z greater than 0. So what I'm going to do now, I'm going to sub this into the part we got in part 4, x plus 1 plus y plus 1 plus z plus 1 is greater than or equal to 3 times the cube root of x plus 1, y plus 1, z plus 1. Cool. So now we have this expression here. And this equality does hold, obviously, since I'm only adjusting what x and y and z were in accordance to what we need to prove. So we can essentially just simplify this a little bit. So we have x plus y plus z plus 3, because we have these 1s there, are greater than or equal to 3 times of this whole thing, okay? And this may look a little bit messy, but we were given that x plus 1 times 1 plus y plus 1 times z is actually equal to 8. So we can just sub that in. So 8, and that's to the power of a third. So now let's simplify this even further. X plus 1, this expression here. Now we can essentially sub this part into that previous part that we had calculated in part 4. Okay, let me write what we're talking about. So part 4, we had that equal to 3 times the cube root of x, y, and z. Okay, so now we see that we have these two similar expressions, and we have the x plus x, y, z that we really wanted. That's what we're trying to prove. And now, what we can do now, how I like working with it is I'm gonna flip this way the expression, and obviously this is just saying that this part is still less than this part because this part is obviously bigger than this part. So that's fine. I can do this. It's fine. And now, what I'm going to do is by using my part, I'm going to say by using star. It's not going to be star. By using star, I'm going to sub this part in. And similarly, I can do the same thing. So 3 is less than x plus y plus z. And now, what I'm going to do, I'm going to sub this part in. So let's come over here. And 3 x, y, z is obviously less than. And I'm going to sub this in now because 3 is less than this. So I'm going to sub in this x plus y plus z. And I'm going to say this is the cube root of this. And then I'm going to say this is less than x plus y plus z y. Cool. And now, it should be pretty clear to see that now we can cancel these off. And what I mean by cancel is we can divide both sides by x plus y plus z, because x plus y plus z is obviously greater than 0. So we defined it to be like that. And now we get that the cube root of x plus x, y, z is greater than or equal to 1, because when we divide this, it becomes 1. And cubing both sides, we get x plus y plus z. Oh, sorry. It's less than, and then this is less than 1, which is exactly what we needed. So that's QED as well.